Okay, we're going to have a look at the multiple choice questions from your calculations booklet. So really make sure that you've done these questions, okay? If you've missed any out because you weren't sure, stop this video right now, go back, do them. Okay, rant over, don't leave multiple choice blank. 392 moles, and we also given some information about the lengths and the sides. So density in grams per centimetre cubed. So there's my units, there's my clue. I want to go from moles into grams. So I'm going to look up the mass of 1 mole of gold on the periodic table, which happens to be 197. Times it by 392, that will get me the total number of grams in that gold bar. Multiplying it 10 by 10 by 40 will give me how many centimetre cubed, and that is 4,000 centimetres cubed. So I'm going to take those two numbers. I want grams per centimetre cubed, so I do mass in grams divided by centimetres cubed, and that's going to get me B, 19.3. So next question. The only thing that's different here from a normal empirical formula is I'm being given a fraction, but that's just like a percentage. So if I know one fraction and there's only two elements, carbon and hydrogen, I know that if carbon is 9/11ths, hydrogen must make up 2/11ths. We're only looking for a ratio, so it really doesn't matter what these numbers are expressed as, fractions, percentages, or whole masses. So I'm going to take those numbers, and they are essentially my mass. So to get mass into moles, I divide by the atomic mass, so I can get a ratio in terms of numbers of moles. And I get 0.0682 for carbon and 0.1818 for hydrogen. So we're trying to get a 1 to something ratio or whole number ratio. So our first step for that is to divide both sides by the smallest number. If I do that, obviously carbon becomes 1. If I divide hydrogen 0.1818 by 0.0682, I get 2.67. Not a whole number, and it's not close. It's not 2.9 or 3.05. So I'm going to see that it looks like thirds, and I'm going to try timesing both sides by 3. I do that, and I'm going to get 3/8. Perfect. That is my mass, or that is my empirical formula, C3H8. Number 3, 240 centimetres cubed of a different gas, and they're room temperature and pressure. So really what you want to do, I definitely know it's not 0.1 moles of gas, but don't leap to those conclusions, because it's very easy to see 240 and try and get that into 24,000. That's actually 0.01. Not the same mass. I want you to try and think of two very similar, like two familiar gases like hydrogen and ammonia, for example. Now you can see if there's the same number of moles, there's definitely not the same amount of mass, okay, because one of those weighs 2 and one of those weighs 17 per mole. So we're left with number of gas molecules, number of atoms. I can see that number of atoms isn't true either, because each molecule contains a different number. Ammonia contains 4 atoms, hydrogen contains 2, so it must be C. Number 4, we've got a mass in grams for sodium chloride, and we've got a volume in centimetres cubed, and we need moles per decimetre cubed for my concentration. So that's the calculation I'm going to do. I'm going to need to turn mass in grams into moles. Checking out on the periodic table, the molecular mass of sodium chloride is 58.5, so it turns out that there is 0.1 moles there. 250 divided by 1,000 will get me my decimetre cubed, so that's 0.25. Pop those numbers in my calculator, and I get the answer B, 0.4 moles per decimetre cubed. Number 5, so a total of 5 decimetre cubed of blood and 140 millimoles per decimetre cubed. That's not a typo, that's millimoles. So what that means is that in every decimetre cubed, there's 140 over 1,000 moles. So that's how I get millimoles into moles. Just think millimetres into metres. So that's my concentration in moles per decimetre cubed. And the total volume is 5 decimetre cubed of blood. So to work out the total mass, I will need to know the total number of moles in that 5 decimetre cubed. So if I take my concentration in moles per decimetre cubed multiplied by the number of decimetre cubed, that will give me the total number of moles, which is 0.7. 0.7 moles. Sodium has an atomic mass of 23. So to turn it in from moles into grams, I would simply do 0.7 times 23, which gives me 16.1 grams, which is A. Number 6 is about atom economy. So you've been given the MR values, which is kind of nice, but you've only been given the MR values for 1 mole, so be careful. The thing that I want in the equation, so my useful product, is going to be ethanol. So I need to make sure that I find ethanol in the equation. There it is. So my total mass of ethanol produced is going to be 2 times 46. So I can already cross off C and D because they don't include the number 46, or rather they don't include 2 times 46. And then it's only ethanol that's useful. The CO2 is not used for anything, so my answer is B. So I'm not including the 44 in that. It's over 180 because 180 is the total mass of the product. Now I could add up 2 times 46 plus 2 times 44 and find 180. Or I could just look at the left-hand side and see that there's only 180 grams going in. Conservation of mass, there's only 180 grams going out. So you don't always need to add up all of the stuff on the right-hand side if you already know the mass on the left-hand side. Number 7. So this time I've got a volume question. So I'm going to use balanced equation and I'm going to relate it to volume, and I want to know the maximum amount of CO2 that could be produced. So just rewriting out the balanced equation, then I can see that I've got the number of moles in front. I could turn that into decimetre cubed because moles is directly proportional. So I could also say it's true that if I had 2 decimetre cubed of CO and react with 1 decimetre cubed of O2, I would make 2 decimetre cubed of CO2. And then I could follow on from that, and I could, just going to move myself because I'm going to get in the way, I could work out that what I could get if I had 5 decimetre cubed and 2 decimetre cubed, but those two numbers don't relate in the same way that 2 and 1 does. So it's not as simple as just saying using one of those numbers. There's a reason I've got 2. This is a limiting reagent. Oxygen is the limiting reagent. So for 2 decimetre cubed of oxygen, only 4 decimetre cubed of CO is going to react because that's the ratio. I can't use my whole 5 decimetre cubed. So only 4 decimetre cubes of carbon monoxide can react with 2 decimetre cubed. The carbon monoxide is in excess. That means the maximum CO2 I can make is also 4 decimetre cubed. That's the maximum I can get from 2 decimetre cubed of oxygen, which is the limiting reagent. So my answer is going to be B, 4 decimetre cubed. Very easy to jump to conclusions with that one. Okay, number 8. So which of those solutions would react with a solution containing 0.05 of sulfuric acid? Sulfuric acid is H2SO4. So when it dissolves in water, it makes 2 moles of hydrogen ions. That's going to be important for this reaction. It's a neutralization reaction. It's the hydrogen ions that are reacting with the hydroxide ions. Hydrogen ions react with hydroxide ions in a 1-to-1 ratio. So what I'm going to do is actually work out the moles of hydrogen ions. There's more than one way to do this, and mathematically, if you got it right, it doesn't matter. However, I'm going to do this because it's going to help you if you're going to do acids and bases and calculations next year. So 0.05 moles of H2SO4 is going to make 0.1 mole of H plus ions. Having done that, I now know that I need basically 0.1 moles of OH minus. So just looking through the questions, or the answers, I can cross off A and B, and that's just because 50 times 1 isn't going to get me anything that looks like 0.1, and neither is 100 times 2, so I can already cross off things that I know are not going to give me 1 in my answer, or 0.1 in this case. So I'm left with C and D. Barium hydroxide is group 2 hydroxide. You're given the formula, so you get 2 hydroxide ions for every 1 mole of barium hydroxide. So 100 divided by 1000 gives me decimeter cubed, times 2, so 0.1 times 2 times 2, because it's barium hydroxide, gives me 0.4 moles of OH minus. That doesn't work. The next one, 50 over 1000 times by 0.1 gives me 0.05 times by 2, because it's barium hydroxide, gives me 0.1 moles. So the answer is going to be D. 2 to do. So number 9. We've got a volume of the sample and a concentration. So 5 centimetre cubed, 1 times 10 to the minus 2. And we've got a final concentration that we want to dilute it down to. This is really useful stuff for the rates of reaction stuff that you might do next year when you have to make dilutions in order to create different reactions at different concentrations. So I'm going to write down the initial concentration that I have in what is sometimes called the stock solution. So you will really see that in practical methods. It will call that the stock, your starting solution. Final concentration I want is 5 times 10 to the minus 4. So I'm now going to use those two numbers to work out how many times I need to dilute the solution by. So what factor, what do I have to basically divide it by in order to get this new lower concentration? So to work out what I'd call the dilution factor, so how many times I'm diluting it down by, how many times I'm going to increase the volume by, I'm going to take my initial concentration and divide it by my final concentration, seeing how many times the final concentration goes into the initial concentration. So it's 20 times, that's my dilution factor, and then that means that my volume needs to be 20 times my initial volume. So if my initial volume is 5 centimetre cubed, then my final volume is going to be 100 centimetres cubed. But be careful about now jumping to conclusions and dropping an answer in there, because the question is not what is the final volume, but what to add. So how you get from 5 to 100 is you add 95 centimetres cubed. Question can be phrased in different ways. Make sure you read it correctly. Okay, number 10, the last one. The number of chloride ions involved. So you need to know about your formulae in this one. You can't just jump to conclusions and do mole calculations straight off. So, for example, aluminium chloride, aluminium is in group 3. Calcium chloride, calcium is in group 2. So they're going to have different formulae. They're going to have different numbers of moles of chloride ions per mole of compound. So per mole of aluminium chloride, there are going to be 3 moles of chloride ion. For calcium chloride per mole, they're going to be 2 moles of chloride ion. And for the last two, just 1 mole each. So now I can go back to the calculations, and there are some things that I can do to make this calculation a little bit quicker because it's only a multiple choice. So what I can spot is that all of the volumes are in centimetres cubed and all of the standard form sections are 10 to the minus 2. So I can effectively ignore those because all I want to know is the biggest number in relation to the others. So like the empirical formula question, I actually don't really care about the units. I just want to know the relative number of moles. So what I can do is, instead of doing 10 over 1,000 to make decimeter cubed, and then timesing that by 3.3 times 10 to the minus 2, is I can actually ignore those numbers. I can ignore dividing by 1,000 because every single one needs to be divided by 1,000. And I can ignore the 10 to the minus 2 because every single one needs to be divided by 2, and I only need to know the biggest number out of the 4. I don't need to know the actual real numbers in moles. If you don't understand why you're doing that, don't do it. Just do work out the moles. It'll take you longer, you get the right answer. So for A, for example, a simple calculation I can do would just be 10 times by 3.3 times by 3. So I've just taken out any issues of working that out, and I get myself 99 moles. It's not obviously not 99 moles, it's a really much smaller number than that. But it's 99 relative to the other numbers. If I now do that with the other ones, 20 times 5 times 2 for calcium chloride, then I'm going to get my number of moles there. And so 20 times 5 times 2 is going to give me 200. The next one, I'm going to do 30 times 3.3 times 1, which is 99 again. And the next one, I'm going to do 40 times 2.5 times 1, which is 100. So we can see that the calcium chloride example is the one with the most moles. So you don't necessarily all the time in a multiple choice, although I'm saying write it down, work it out, you don't necessarily need to write down everything and work out everything in order to eliminate things and to get the right answer. In other times, if you're doing a longer situation with the more structured calculations, clearly you want to make sure that you're actually working everything out and you're doing it to the right unit, so you would genuinely work out moles in that situation. Okay, I hope you really enjoyed those. Any more multiple choice questions that you want? Obviously you can find some on things like Physics and Maths Tutor. A really good place for multiple choice questions would be actually to look at the International Baccalaureate papers. So they're not exactly the same chemistry all the time. There are a couple of differences in the syllabus, but very little. And actually they've been doing full multiple choice questions for years. And so there's like huge banks of them to have you have a look for online for International Baccalaureate chemistry papers. That's my top tip for more multiple choice practice. Okay, see you soon. Next thing we're going to be looking at will be Hess cycle and energetics calculations. So we're not getting a break from calculations this week.